Hello. In this video lecture, I will be covering both chapters 15 and 16. In those two chapters, there are four major topics that I'm going to be talking about. The ideal gas law, the kinetic theory of gases, the first law of thermodynamics, and the second law of thermodynamics. There's a lot of stuff to be covered. The two chapters combined contains a lot of information, so I am going to be skipping certain parts on those two chapters. Probably we're going to be covering 60 to 70% of it. Please use this video lecture as a guide of what is covered or what you need to know. Excuse me. Anything that I don't mention in this video lecture, you can safely skip it. Okay? To begin with, I am going to give you a brief review of things that you have studied in chemistry, and that is especially atoms and moles and the atomic mass number. So let me talk about that for a bit before we go into the ideal gas law. Atoms and moles. As you all know, we have something called the atomic mass number. The atomic mass number is basically the number of protons and neutrons in an atom. So, and it has the symbol A, and it is basically the number of protons, Z, plus the number of neutrons. The number of proton is called in chemistry and in physics as well, is called the atomic number, right? And the A here is the atomic mass number. So the word mass there is mentioned. So that's the mass number, or the atomic mass number, okay? And this atomic mass number doesn't just give you information about the number of proton or the sum of the proton and the neutron. It also gives you the mass of this atom in comparison to the mass of the carbon atom, if you remember from your chemistry class. Let me just show you a periodic table here. I just pulled it out from Wikipedia, so I'm sure you're familiar with it. So, for example, hydrogen here. If you look at hydrogen 1, helium 2, lithium 3, beryllium 4, and so on, these numbers, 1, 2, 3, 4, and so on, are the atomic number, which is the number of protons. So, for example, beryllium contains 4 protons, and say carbon contains 6 protons, and so on. Of course, you subtract that from the atomic mass number to get the neutron. And then the number below it right there, okay? These numbers are the atomic mass number, which is basically the addition of the number of protons plus the number of neutrons. Of course, as you can see, they are in fractions because you are including the masses of the electrons as well. But again, that's also chemistry. We're not going to worry too much about that. So, for example, let me just, how do I magnify this thing? Oh, there. So, there we go. Let's say, for example, I'll make it a full page. It's not working. Anyway, so for example, if you look at hydrogen here, so the atomic number is 1 and the atomic mass number is 1.008. This is A, the value A, or the atomic mass number, okay? Now, your book uses basically A, just basically approximates it into the closest nearest number, and that is A, 1. For helium, it is 4, according to our textbook. Carbon, even though it's 12.011, it is 12, and so on. For oxygen, we have a couple of examples to talk about oxygen. In the periodic table, it's 15.999. In our book, we just use 16, and so on. You got it? So, okay. So, for hydrogen, for example, the mass of hydrogen is hydrogen 1, that is, which means just one atom of hydrogen. The exact number is 1.0078 atomic mass unit, AMU. okay? And for example, for helium, again, just one atom of helium, not two, not a molecule or so, and that would be 4 AMU and so on. So our book here approximate that to be 1 AMU. We got that? And of course, our book also approximated to be, well, this is already 4. For oxygen, for example, oxygen, let's say O2, which is the molecule. This is molecule oxygen, which means 2 oxygen atoms are bonded together. So each of them has 16 according to the periodic table, right? So that will be the mass of O16 plus the mass of oxygen 16, and that will give you the molecule is 16 plus 16, and that will be 32 AMU, okay? And so on. Okay, the AMU here is a unit, as you know, that is a mass of an atom in comparison to the mass of the carbon atom. Okay, we use carbon to be exactly 12 AMU, and then what are the masses of other atoms as compared to the 12 AMU of the carbon, okay, and so on. So we have the conversion factor. Let me look it up. 1 AMU, just in case if you need it, 1 AMU atomic mass unit is equal to 1.66 times 10 to the negative 27 kilogram, okay? I'm sure your chemistry teacher gave you this conversion in gram, but there it is, okay? And another thing that we studied in chemistry is the mole. And as you know, 1 mole of matter is the amount of substance contained in 12 grams of carbon, right? So 1 mole is equal to Avogadro's number, 6.02 times 10 to the 23 particles, atoms, molecule, whatever you're dealing with. So we just call them particles here. Okay, and that's the Avogadro's number. We're going to use the symbol N, capital N sub A for Avogadro's number. Okay, that's another number you want to keep in mind. So let me give you just a quick example, show you how all this works. Let's say I have a mass of 100 gram of oxygen gas, okay? So I have a mass of 100 gram of oxygen gas, and the question is how many moles? Okay, I hope this is an easy question for those of you who have taken chemistry. So we know that, of course, we're assuming here oxygen gas molecules, okay? So that means it is O2, not O1. You see what I'm saying? Okay, so let's assume it is 1 molecule. Okay, if we assume that, so first thing I need to do is I want to, so for O, here we have, it is 16, the atomic mass is 16 AMU. Is that right? So for O2, it is 32 AMU. And what I want to do, one way to do it, is I want to convert it into kilograms. So to convert that, put this over 1, put AMU here at the bottom so you can cancel it, and this is kilogram, and that would be 1.66 times 10 to the negative 27, and then when I do the calculation, I will get 5.31 times 10 to the negative 26 kilogram, okay? So in other words, for 32 atomic masses of oxygen molecule is equivalent to this in kilogram. Why did I convert it to kilogram? Because I already have the mass of the sample in gram. I want to convert this to kilogram. So I want to compare the two in terms of kilogram rather than AMU. You see what I'm saying? Okay, so now the mass of the sample that I have, the oxygen, is 100 gram. Again, your chemistry would use gram, where we use kilogram here in physics, so it's just going to be 0.1 kilogram. And now I have, this is the atomic mass right here, right? And this is the mass of my sample that I have. And from those two, I can be able to find the number of moles, okay? But before I do that, I need to get how many, remember, because this is a, the atomic mass of the molecule, I know it is equal to Avogadro's number, you see what I'm saying? So I want to know what is the number of particles or molecules in here, you see what I'm saying? So one way to do that is to say that the number of particles n is equal to the mass of the sample that I have divided by the atomic mass. Atomic mass. Of course, the atomic mass of the molecule here, okay, oxygen molecule. So that's going to be the mass of the sample is 0.1 divided by 5.31 times 10 to the negative 26. And when I calculate that, let me use my calculator. 0.1 by negative 26, I get 1.88 times 10 to the power of 24. Okay, particles. You got it? So now we know that the number of moles is n over the ratio of the number of particles in my sample to Avogadro's number. So that will be equal to 1.88 times 10 to the positive 24 divided by Avogadro's number, which is 6.02 times 10 to the 23. And when I calculate that, I get 3.13 moles. You got it? Okay. Let me see if I can find. I think that's good enough. I hope you'll find this stuff easy for you, especially for those who've taken chemistry. All right. Let me just begin with our lesson with this review, and we begin with the ideal gas law, or the ideal gas. And I assume some of you have already taken those lessons probably in your chemistry class as well. Okay. So what is an ideal gas? An ideal gas is a gas that is composed of small random moving atoms that bounce with each other and with the wall of the container. But when they collide with each other, they do not interact with each other. In other words, when they collide, they don't bond with each other, for example, or other particles come out of it as a result of the interaction between them. So, in other words, let's assume that I have a sample. Let's say I have this small container that has an ideal gas, and let's assume that in this within this volume I have, say, 2 particles, and those particles are moving in random motion. So this particle is moving this way and this particle is moving this way. So now if I follow the motion of this particle, is going like that, and it's all over the place and so on, you see what I'm saying? And then this particle is going again, is going this way, and it's bouncing off, and it's going all over the place. As you can see here, because you only have 2 particles, and because you have 2 particles here, and the volume that they are in is extremely large compared to their sizes, the probability of them actually colliding with each other is very, very low. I mean, it's there, it's not 0, but it's very, very low. Okay, that's one thing. Second, even if they collide, they're not going to interact with each other. In other words, they're not going to bond, or they're not going to break apart and form if there are 2 molecules, they're not going to disintegrate into different other molecules or other atoms or whatever. So there is no interaction whatsoever between them. Okay, so this kind of gas that we have, where the sample, the number of atoms in it is very, very low, the density is very low, we refer to it as the ideal gas. You got that? So there are really three conditions for the ideal gas. One is that there is not much interaction between them. Two, the density is very low. Okay, in other words, the atoms occupy a much smaller volume than the volume of the volume of the container. And three, another one is that the temperature is within this container, within the volume here, is well above the condensation point, because if it is low enough to the condensation, that means it's going to melt, and therefore those atoms are going to be interacting with each other. So anyway, that's basically what the ideal gas is. As a result of that, because we are imagining this ideal gas, there is a nice formula that describes this ideal gas. It's called the ideal gas formula, and it is equal to PV equals nRT. I'm sure you've seen it before, where here P here is the pressure, V is the volume, and N here is the number of moles. R is a constant. It's called universal gas constant. And it is equal to 8.314. I forgot what the unit is. Let me look it up. It is joule per mole Kelvin. Okay, that's called the ideal gas, universal gas constant, rather. Okay, and of course T here is the temperature. Okay. Let me just talk a little bit about this formula. When we say PV, well, what is the nature of it? Is it energy? Does it describe energy? Does it describe force? What is it? What is that thing? Well, let me explain it to you. Let's say I have a cylinder with a piston in it, like that. Okay, it's a piston system, and I have inside of it gas, ideal gas, that is. Okay, and let's assume that I would pull the piston. Sorry, let's assume that I measure the volume of the container or the piston here, and let's assume it is some initial value V1, and I measure the pressure to be P1 at some temperature T1. We call that PVT. Okay, so I prepare the system at a certain PVT. Okay, now let's assume that I'm gonna pull the piston upward like this with a force. Okay, so now the piston looks something like that. Here is the cylinder, and now the piston is a little bit above, right here. Okay, and now the gas has more space to expand into. You see what I'm saying? So now I have a new volume, V2, a new pressure, probably less, P2, and a new temperature, T2. You got that? Okay. So what have I done? Well, I have exerted a force F on it. See what I'm saying? In other words, the piston was, the original position of the piston, let's assume it was right here. Right, this is the original position of the piston, and I exerted a force on it, so it has moved this much distance. Let's call it delta y. Okay, this much with it. So what I have done work on it, and this work that I have done, of course, is equal to the force times the displacement. The displacement here in the vertical direction, and I'm just going to call it delta y. Okay, and I know that pressure is force per area. Area of what? Well, it's area of the piston. This is the piston right here. Okay, the area of the bottom of the piston right there is A. Okay, so in this case, the force is P times A. Correct? Now I can take this and plug it back into the work formula right there. So the work becomes P times A times delta y. But what is A delta y? Notice that, go back to the second diagram here. So the area of the piston is right here at the bottom, or this one here, and then you have the delta y is that. So A delta y is basically the volume, the increase in volume, let's say, delta V, you see that? So A delta y is delta V. So work, this is a new formula that you may have not seen before for the work. We said that we always learned that work is equal to F delta y, Fx, or the change in kinetic energy, if you remember, or the change in potential energy. Well, we have a fourth one here. Work is pressure times the change in volume, okay? So when I go back to the ideal gas law, it says PV. Well, what is PV? It's work. See that? So PV is work, really. It really calculates the work. And then nRT, well, since this quantity is equal to this quantity, nRT is also work. Just another way of calculating work. So the left-hand side and the right-hand side of this equation basically describe the work. Got that? Energy, basically, nRT. So nRT and PV are work. This is something to keep in mind. Okay, good. There is something else before I move any further about this equation, and that is what is called the PV diagram. This is very important, the PV diagram. So what is that? Well, the PV diagram is basically, think of like X and Y axis, but then this time we're going to have a PV axis, like that, where this is the volume. The volume is always on the horizontal axis, and the pressure, P, is on the vertical axis, like here, all right? And then you have something going on here, okay? Some process happening. For example, let's say I prepare, let's go back to my piston here, and we said that I have prepared my piston to be at a certain PVT, which is V1, P1, T1, right? So if I am going to represent the PVT here with the PV in the PV diagram, it's going to be some dot right here. So this dot at this is at some V1 and at a some P1. You see what I'm saying? The diagram doesn't give you the T, the temperature. However, you can obtain it from the PV equals nRT. You see what I'm saying? In other words, if you know V and you know P automatic, nRT, you will automatically know what T is, okay? So the diagram doesn't give you information about the temperature, but you can always find it using the ideal gas law. Get that? Okay, remember N and R are basically constant. This is just the number of moles in the gas that you're dealing with. And most of the time it's constant. You're not assuming that the gas is not leaking out of a piston or something like that. And then you get R. R is just a constant, 8.314 and so on. Okay, so you can always find the temperature. So anyway, so I prepare the system to be at a certain V1, P1, T1, and this dot right here is represented by it. And now what happened? Well, what happened is that I have increased the volume of it, which I've done work on it, right, with the force pulling it, and the temperature have changed, and the volume have changed. And let's assume that as a result of that, now the system is right here. It's represented by this point. Okay, this is V2 at a certain P2. You see what I'm saying? Now, what we are interested in is the process. How did we go from here to here? We could go like this. We could go directly this way. We could go like this. And there are really infinite number of paths that you can take. You see what I'm saying? But this is the subject that we're going to be talking about, is that how did we start from say, point 1 to state, it's called state 1, thermal state 1 to thermal state 2, okay? We're going to be talking about that later in this lecture, okay? So that's basically what you need to know as far as the PV diagram is concerned. All right. Let me do an example before I go any further. this is all from my notes. So the example says I have oxygen, O2, oxygen gas, okay? It's all gas, okay? Never liquid or anything like that. So oxygen gas, O2, of mass 100 grams, okay? In a container with initial volume, we're going to call it V. No need for the initial volume, just with a volume, sorry, with a volume, I'm thinking of another problem, with a volume of 600 centimeter cubed, watch those units, and temperature of 150 degrees Celsius, okay? The question is, find the pressure. Okay, in other words, if I have oxygen gas of 100 grams, okay, just the same as sample that we dealt with just a minute ago, 100 grams, and it is contained within 600 centimeter cubed of volume, and I am preparing it to be at a certain temperature, 150 degrees Celsius. Don't forget to convert it to Kelvin. What is the corresponding pressure? Well, it doesn't sound difficult, does it? You can just use PV equals nRT. So we go PV equals nRT, and then we can just plug it in because I know the volume right here. I just need to convert it to meter cubed. I can just plug it in there. I know the temperature, just add 273 to make it into Kelvin. I can plug it in there. R is just universal gas constant, 8.31. And then we can plug in, but we still have one problem, and that is what is the number of moles. So we have to find the number of moles. We have done that just a minute ago, if you remember. So let me go over it very quickly. So we have 16 grams of oxygen give me 1 mole, right? So for 100 grams, how many moles, right? That's really what I'm looking for. So the number of moles in this case is going to be basically cross-multiply. That'd be a quick way of doing it, like that. Cross-multiply this way equals this times that. That would be one way to do it. That's how I do it. So it's just going to be, how do I do this? Hold on. Let me just do it my way first. So it's going to be 1 mole, that is, times 100 grams equals n times 16 grams, and then just solve for n. N in this case will be equal to 1 times 100 over 16. So the number of moles in this case is 6.25 moles. But remember, this is what number of moles for atoms, you know, atomic mass for oxygen. But here we have molecules, O2. So basically I'm going to divide this by 2 because each pair is bonded. So this is the number of moles for individual atom, oxygen atoms, but all of them are paired up. So that means you're going to divide it by 2. So basically the number of moles really is 6.25 divided by 2, and that will be 3.125 moles for molecules. You got that? Okay. Okay, so we got the number of moles right here. Okay, and then I just go back and then I just plug it into my ideal gas law. So that's P is equal to nRT divided by V, and I have everything here. So when I plug it in, I have number of moles is 3.125 times 8.314 times, oh, I forgot to, so that will be 150 plus 273, is that right, guys? Divided by the volume is given to us, and it is 600 centimeter cubed, so that means 600 and the centi to the third, that makes it 600 times 10 to the negative 6, is that right? So it's going to be 600 times 10 to the negative 6 meter cubed, and then you just calculate all of that. And then when you calculate it, I have the answer in front of me, 1.83 times 10 to the power of 7. And what's the unit of pressure? Pascal. Don't forget that, the Pascal. Okay. Now, I can convert it into ATM. 1.83 times 10 to the 7 divided by how many, what is it? 1 ATM is 1.015 times 10 to the 5th Pascal. Go back to my previous video lecture of chapter 14. We talked about that. So you can just convert to 1.013 or 5. I think it's 3, isn't it? Times 10 to the 4. Yeah, I think it's 3. And then you divide that, and you will end up getting divided by 1.0135 equals 181 ATM, which is huge pressure. You see what I'm saying? We live under 1 ATM right now, and this is under a huge pressure, 181. Got it? Okay. One more problem. I got, I think, at least two more. Again, I think you've seen all of that in your chemistry class. So hopefully this subject, at least part of it, is easy for you, I hope. All right, here's another example. And I know chemists cover this in more extensively at a higher level than what we cover it in physics. All right, it says here we have a pure helium. Helium, I can't spell it. If I can erase this thing, won't erase. There we go. Pure helium gas. And helium doesn't bond into molecules, so we're just going to assume these are helium atoms. So pure helium gas inside a cylinder or cylinder piston system, that is. Initial PVT is, we have a volume of 15 liters, pressure of 2 ATM. As you can see, these are all wrong units for us. Temperature 300 Kelvin. Now it says if the volume is decreased to 12 liters and pressure, so what will happen when you decrease the volume? The pressure will go up. Make sense? Because you're pressing it. So the pressure increase to 3.5 ATM. Okay? Question, what is the final temperature? Okay, what is the final temperature? Okay, now it sounds like a hard problem, but it's not. What you do is the following. See, if you prepare the system to be in a certain condition, some certain PVT, pressure, temperature, volume, and then you vary the system. You heat it up to change the temperature, or you press it, decrease the volume and increase the pressure, and whatever. You can compare, and then you're asked to find what is the resulting temperature or the resulting volume, whatever. You can actually use the ideal gas law in a smart way. Here's how it works. Let me show you. So we know that PV equals nRT. Okay. Now, if no leakage, for example, if there is no loss in the mass of the helium, okay. In other words, the piston here wasn't leaking helium, which is not. That means the number of moles is constant. Okay? So what I could do, watch this. So I can take this T and put it on the other side. So it becomes like that. PV over T equals NR. But NR is a constant, correct? So that means PV over T is always constant. As long as there is no loss in mass. So I can write this formula like this. P1 V1 over T1 is equal to P2 V2 over T2. And that's a really important formula to keep in mind. Okay? So basically, this is the first condition. When I prepare the system to be in a certain PVT, then I've done something else to it, and then he's asking me what is the temperature. Well, I can just use this formula. You understand? So let's look it up. So yeah, what we have, and by the way, you don't need to convert units if you don't want to, because they'll cancel out anyway. Even if you convert them, you'll end up getting the same answer. So anyway, so let's look at the first condition. He said, so I have a pure helium gas inside a cylinder piston system, initially at those. So I'm going to call these V1, P1, T1. See what I'm saying? So here I have, so let me just copy them and put them right here. So that's going to be P1, and that's going to be 2. V1 is 15 divided by T, always in Kelvin, never ever put it in Celsius. So it's 300 equals to, what's going on? He said the volume decreased to 12. So now the volume is 12. You remember, from 15 to 12. You see what I'm saying? And then the pressure, he said, increased to 3.5 divided by T2. There we go. See how easy it is? As you can see, the reason I didn't convert the units is because even if I said here 12 liters and this is 15 liters, you can see it'll cancel out. You see what I'm saying? Same thing with ATM and ATM and so on. So that's why I didn't bother to convert. Okay. All we need to do is just to solve for T2. So when I solve for it, it's going to be 3.5 times 12 times 300, cross multiplying it, that's what I'm doing, over 2 times 15. Okay. And then we do the calculation with that, and you'll end up getting 420 Kelvin. And there we go. Got it? Okay. Let me tell you this story very quickly. So here is how this problem works. I am starting with, here is the piston, here's the handle, and so here it is, the system here at a certain P1, V1, T1, correct? And now what I've done, I compressed it, or rather, I decreased the volume up to, so way down, what it, let's say, is here now. So it went down this way, okay? So now I have a new P2, P2, V2, and T2. So what happened when you decrease the volume, the pressure increases. It makes sense, right? You're kind of compressing it. Okay, so what is the corresponding temperature? The temperature should be more, right? You're starting with 300, so the temperature should be more. My common sense tells me that. There we go, it's 420. You got that? Okay. One more problem. It says, I have a sealed glass bottle. Okay. At temperature 27 degrees Celsius, okay, contains air at 1 atm. Okay, basically the regular pressure that we live under right now, and has a volume of 30 centimeter cubed, okay? 30 centimeter cubed. I'm trying to fix that 3. Today is not erasing very well. Forget it. Okay, now the bottle is tossed into open fire. Okay. And the temperature reaches 200 degrees Celsius. Question: what is the pressure inside? Kind of similar to what we have just done, right? Okay, so what makes it a little bit different from the previous problem? What makes it different is that the volume here of the bottle didn't change. See, it says a sealed glass bottle, which means this bottle's volume is not changing at all. It has initially it has air at 27 degrees, which is basically room temperature. So I take that and I throw it in the open fire, and what will happen that the air inside heats up to 200. Okay, remember 100 degrees is the boiling temperature of water. 200 is double that, so it's extremely hot. So you would imagine that the pressure is extremely large inside. I mean, if the bottle is not thick enough of glass, it may explode. You see what I'm saying? So now he's asking, what is the corresponding pressure? Well, we use the same formula that we have just used, which is P1 V1 over T1 equal P2 V2 over T2. The good news here is that the volume in both situations is the same. So that means the V1 and V2 will cancel out each other. You see what I'm saying? So I end up with P1 over T1 equals to P2 over T2. And then he's asking for the pressure inside, the new pressure, which is P2. So P2 in this case, just do the algebra, cross multiply. So P2 in this case is going to be T2 over T1 times P1. That's the formula that we're going to be using. Again, be very careful. Always convert to Kelvin when it comes to temperature. Now you may say, let me show you a mistake that you may make. Some student may, not you. Look, I have T2 over T1 here. Do you see that right here? And you say, oh, well, I can just use Celsius because the units are going to cancel. This doesn't work that way. It works for anything else, but it doesn't work for Celsius. Here, watch. If I have T2, which is 200, and the other one is 27, when I calculate that, remember this is wrong, okay? So it's going to be 200 divided by 27. Answer, you get 7.4, right? Now, when I convert it into Kelvin, which means 200 plus 273 divided by 27 plus 273, you're not going to get that ratio here. No way. So it's going to be 200 divided by 273. Answer, oops, I think I made a mistake. 200 plus 273 is 473 divided by 27 divided by 273 is 300. I keep making the same mistakes. 300. And when I 473 divided by 300, and the answer is 1.58. As you can see, is not the same. So always, always, always convert Celsius into Kelvin. Okay. Only condition that you don't do it if you have a delta, just like we talked about in the previous video lecture, chapter 14. Okay. So you have to do that. All right. So we have here P2 is equal to what do we have? 473 divided by 300, right? Time the pressure. He gives us the pressure. Oh, he said 1 atm, correct? Shall we keep it in 1 atm? Sure, if you want to end the answer with atm, in terms of atm, so let's leave it that. You can convert it into Pascal, but maybe he wanted to in atm. So as we did for this ratio, it's 1.58 right here. So it's basically 1.58 atm. So that's the new answer, or the new pressure, rather. Okay, got it, everyone? Okay. There is another version for the another useful version for the ideal gas law, ideal gas formula. Oops, formula. My eraser quit working. I had to restart OneNote to get the eraser to work. So anyway, I'm back. Okay, it says another useful version for, there we go, it's working good. Version for the ideal gas formula. Okay, so we said that PV equals nRT. This is the formula that we dealt with. We also said in the beginning of the lecture that the number of moles is basically the number of particles or atoms in the sample divided by Avogadro's law. So I can take this and replace it with small n right here. So in this case, PV is equal to n over Avogadro's law RT. Now, as you know, the R here is the universal gas constant, and n sub a here is Avogadro's number. So if I take the ratio of those two, okay, and we define this ratio as what is called the Boltzmann constant. So it becomes n, and the Boltzmann constant K sub B T. So here K sub B is the Boltzmann constant, or the gas constant. Okay, and this gas constant, K sub B, is equal to 1.38 times 10 to the negative 23 joule Kelvin. Got it? Okay, so that's just another version for it. Sometimes it comes in handy, so you may want to use that. Okay? Okay, good. The next topic that I want to talk about is the kinetic theory of gases. Please take the time to read the section about the kinetic theory of gases. I'm just going to talk about the result of that and maybe one or a couple of examples of it. One example, the kinetic theory of gases. And it basically, there is a lot of derivation to the formula that I'm going to show you. You don't need to know that derivation. But basically, it boils down to one particular formula that is a remarkable formula. It's one of the most important formula that came out in physics in the late 19th century. But basically the formula says that the temperature is proportional to the average molecular kinetic energy. Okay? Temperature, let me write it down. Temperature is proportional to the kinetic energy of the atoms or the molecules. Okay? What does that mean? It means the following. It basically tells you what the difference between heat and temperature. I'm sure you've heard of that before. Heat is energy, or the amount of energy in a substance. For example, when I say this cup of coffee is hot, what I'm saying by the word hot here is that it has a lot of thermal energy inside of it. Okay, and that's the real, energy. Now, when I say the temperature of the cup of coffee is 70 degrees Celsius, the difference between this 70 degrees Celsius and hot cup of coffee, or heat, the heat contained in it, is that the molecules that make up the coffee molecules, if you will, okay, they are interacting, they are moving very rapidly in colliding with each other and colliding with the wall of the container, the cup, okay, very rapidly with a kinetic energy. That kinetic energy corresponds to what we call the temperature. So in other words, the 70 degrees Celsius gives you information about what is the kinetic energy of those molecules. You got that? And so you come up with this equation after we do this derivation. Very remarkable equation, like I said. It says 1/2 mv bar squared is equal to 3/2 K sub B, the Boltzmann constant, times T. Look at that. See, in other words, if I am, let me change the color. So if I want to know, if I have, this is the temperature right here. This temperature basically gives me information about the motion of those molecules, the speed of those molecules. You see that? Remember, 1/2 mv squared is just kinetic energy, as you can see. Average, the bar here means average, okay? So the average kinetic energy of that molecule. So the temperature gives me information about the kinetic energy. In other words, the temperature is nothing but the thermal kinetic energy of those atoms or molecules. Okay. Another thing, so let me just write it down here. So this one is, this says that the temperature is but the measure of the kinetic energy of the molecules. Okay. We also have something else, and that is if you solve for the V here, okay? If you solve for it, it becomes V bar squared is equal to, if I'm going to solve for it algebraically, the 2's cancel out, as you can see, and it becomes 3k sub b t, sorry, let me take that square out. I just want a V bar. Divided by the mass under the root like that. Okay? And we refer to this as the root mean square speed, RMS. Okay? So the RMS speed here is, or the square root of V bar squared, you see what I'm saying, is equal to this value. The RMS is basically analogous to the average value, okay, except it's slightly larger in value. Okay. And one last thing before I give you an example on how all of that works. This formula here is basically you can calculate the average kinetic energy for one molecule. In other words, if I say the temperature of the coffee is 70 degrees Celsius, and then I put in that 70 degree, of course, converted into Kelvin here, and then I find the VRMS, okay, the average value, it basically tells me what is the average velocity or average speed of one molecule inside that coffee cup, okay? However, if I ask the question, what is the amount of heat, all of the heat, the total internal kinetic energy of the cup of coffee, total internal energy, we calculate in the following manner. It's very simple. What you do is, since we have n number of molecules, right? So in this case, the total internal kinetic energy, okay? Oops, energy, I wanted to say total kinetic energy. Kinetic energy E is equal to N times each kinetic energy of, kinetic energy of each molecule. So it's going to be 1/2 mv bar squared for every single molecule. Or I can take that n and put it right on the right-hand side of this equation. So it's going to be something like 3/2 n kb, k sub b, t. Okay? Either equation will work fine, depending on what you have in the problem, what's given to you. But that's basically, it will calculate for you the total internal kinetic energy. Got it? Okay. I'll give you an example and show what that means. And don't expect a harder problem than the one I'm just going to show you. Okay? So let's say I have a tank contains 2 moles of helium gas at 20 degrees Celsius. Okay? There are 2 questions. A, what is the total internal kinetic energy of the molecules? kinetic energy of the molecules of the helium. Or atoms. I think I should say atoms for helium. I'm not sure if they bond together, to be honest with you. I'm not a chemist, I don't know. Let's just say for the atoms, for the helium atom. So how do we calculate that? Well, here is the formula right here. The one that is probably more suitable for us is the second one here. We only need to find the number of molecules here, but I'll show you a trick. Okay, so we have here E equal 3/2 capital N K sub B T. But watch this. If you remember, let me go back to the version of that it is right here. Remember we said that NKBT, remember this is the ideal gas law, and we said PV equals nRT or PV equals NKBT. Well, NKBT is right there, right here. NKBT right there. So I can replace it with nRT. Why this one? Because he gives me the number of moles. You see what I'm saying? So let me go back first to this equation right here, the one I just wrote here. So I can add another form for it, and that is capital N nRT. NKBT. Sorry, I think I'm messing up here. NKBT, that's going to be 3/2 nRT, correct? There we go. So that's another version for it. Okay, so we have 3 of them that will help you calculate the total internal energy. So 3/2 nRT, or 3/2 NKBT, or N1/2 mV bar squared. Okay, depends on what's given to you in the problem. But keep those in mind. Okay, so if I go back to this one, so I can use this, but it's a shorthand way would be just simply 3/2 nRT. Why? Because he gives me the number of moles, small n, and he gives me the temperature. And of course, we want to convert it to Kelvin, and that's it. Plug it in. So I have here 3/2. Number of moles is 2. R is the universal gas constant, 8.314, and the temperature is 20 plus 273. See what I'm saying? And you just calculate all of that. And when we do that, you're going to end up with 7.3 times 10 to the power of 3 joules. There we go. So that's the total amount of heat, if you will. Okay? This is the total amount of heat contained in that helium gas of 2 moles. You got that? At 20 degrees Celsius, that is. Okay, good. Part B, the last one, he says, what is the average kinetic energy per molecule? What is the average kinetic energy per molecule? Molecule, not molecular. There we go. Okay. So all you need to do is you divide that by n, right? So here we have, this is one way to do it, is we have this version right here, or we can use the one I just showed you right there, this one here, this one here, and I think we got everything. So we can just say the total, the average kinetic energy per molecule, 1/2 mV bar squared is equal to 3/2 K sub BT. So that's 3/2. K sub B is the Boltzmann constant, and it's equal to 1.38 times 10 to the negative 23 times the temperature. It's 20 plus 273, that makes it 293, right? And then we just calculate that, and that will be equal to 6.1 times 10 to the power of negative 21 joule. That's for each molecule. You see what I'm saying? So kinetic energy per molecule here is really tiny number, okay, for that one single molecule or atom of helium. You got it? Okay, good. Next. Okay, now we move to the next topic, and that is the first law of thermodynamics. The first law of thermodynamics is nothing but a statement of conservation of energy, taking into account how the system's internal energy changes. Okay, if you remember when we talked about when we were covering mechanical energy, and I think chapter 4 or 5 or something like that, we said that the total energy of the system is kinetic plus potential energy. Remember that? This is all correct. This is about mechanical energy, but we are assuming here that there is no heat extraction involved. You see what I'm saying? So once you start adding heat to the system, it becomes a thermodynamic system. So this formula here is fine for a dynamical system, but when you start adding heat to it, then you have to include that how the system changes, how the system's internal energy changes with that inclusion of heat. Okay, so in this case there will be some this formula no longer is good enough for our calculation, because you have to incorporate or take heat into account here. Okay, so again, first law of thermodynamics is nothing but a statement of the conservation of energy, including the internal energy of the system. Now, energy can be transferred to the system. When we talk about energy here in those topics, we are really, what we mean is heat energy. Okay, so when I say energy here and you say is it kinetic or potential, well, it's actually heat. Okay, we are exclusively talking about heat here. So anyway, heat can be transferred to the system or between the system, out of the system, in two different ways. One is by either doing work on the system, and in that case heat will be transferred to it. In other words, the temperature of that system will rise, or we can actually use molecular motion, or let's say flame, to add it to the system. Let me explain. I'm having difficulty expressing myself. Okay, let's say for example I have a cylinder piston system here. Okay, and here is the piston, and again I am preparing the system at a certain PVT, correct? So here it is. Here is the gas. Okay, and initially right now it is at a certain PV and T. Okay, some PVT. Now, think about it. If I would, let's say, I take the handle here and I push the piston with a force, and now the piston comes down to here. Okay, remember that. Let's assume that I have a thermometer hooked up to the gas here, so it constantly measures the temperature of it. Okay, so when I push it down like this, okay, what's going to happen to the temperature of the system? Well, what will happen is that's going to rise. So somehow heat has been added to the system. Well, where did that heat come from? It came from the work that I have done. Remember we said that work is equal to P delta V, where P here is basically the pressure, and the pressure is what is FA, correct? I'm sorry, F over A, right? F over A. And F here is basically the force that I'm exerting on the piston to push it. A is the area of the piston underneath, and then delta V. You see what I'm saying? So by doing work here, so I know that delta V is A delta Y, so it becomes F delta Y, which is what we've talked about in the beginning of this video. So I have done work. So what happened here is that I have increased the temperature of the gas by doing work. So work here allowed me to get heat into the system. You get that? So that's one way to do it. So there are, as I told you, there are two ways. One is work done on the system, and the second one is simply, let me go back to the same piston. It's in its original state, right here. Here is the piston. I can simply, what I could do, if I want to add heat to it, I can simply just put an open flame here. Here is a flame. Oops. Trying to make a candle flame. There we go. And I just put heat in here. In other words, I can add heat here, heat it up, put it on a stove, if you will. You see what I'm saying? And what's going to happen? Well, the temperature here is going to rise. Remember, I prepare it in a certain PVT, P naught, V naught, T naught here. And then now, as a result, but when I add heat to it, say put it on a stove, as a result of that, I have added heat to the system. So there are two ways to do it. One way by doing work, and the other one is by actually adding heat to the system. You got that? Okay, so let's look at one of them. Let's look at the second one, for example. So I have added heat to the system. Let me take all of that and just put it into symbolically. So what I'm going to do, I'm going to add heat, and we have a symbol of Q for heat, okay? We talked about that last chapter. So I'm going to add heat. Okay? So what's going to happen when I add heat? Well, what will happen, the temperature of the gas will increase. Okay? And as a result of that, it's going to push the system up. And the system is going to move up. You see what I'm saying? So the piston is going to move up, let's say, up to here. Here it is. So what the heat did to the system is that it has done work to it. Make sense? Because remember, any change of volume, there is work. So work correspond to change in volume. Keep that in mind. It's very important. We'll come back to it later on when we start working on some thermodynamic processes. But this is very important. So what happened is that I have added heat to the system, Q. You know, I put it on the stove. As a result of that, the gas expands, right? Gas expands. Gas, as a result of that, does work by pushing the piston. See what I'm saying? And temperature of the gas rises. You get that? Everybody understand that? Okay. These are very important processes that is happening when I add heat to the system. So what's happening is this. This Q has been distributed. Part of it went into work. And part of it has been given off to the gas to raise its temperature, right? We call that the internal energy delta U, okay? So delta U is the internal energy. And when we say the internal energy, we mean here temperature, okay? So temperature and internal energy is directly related. If I increase the temperature of a gas or water or whatever I'm dealing with, I have basically increased the internal energy. So think of a temperature and internal energy are. So here we just said work and change in volume, and then we have here internal energy, temperature with internal energy. Okay, these are two words that are related, directly related to each other. Okay, but I hope everyone understands what's going on here. Let me repeat it again. The heat, I have added heat to the gas, correct? What happened to the gas? The gas expands because I have added heat to it. As a result of that, when gas expands means that the gas does work by pushing the piston up, right? By pushing the piston up. Okay? And in addition to that, that heat also, in other words, part of it went into work by pushing the piston up, and the other part of that heat went into raising the temperature of the gas. Okay, so those two. So that means the total amount of heat added, part of it went for doing work by pushing the piston up, and the other part increased the temperature. Okay, and guess what? This is the statement of the first law of thermodynamics. First law of very, very important statement, okay? And usually we write it this way. The change in internal energy is equal to Q minus W. This is the version that I'm going to be using. Okay, so write it down before you move on. Let me show you examples, some examples to help you understand this formula. Looking for one. Okay. Well, before I do the example, sorry, let me just give you some more information on it, and then we'll do a bunch of examples on this. There are different thermodynamic processes that can be done. I'm going to go over them briefly, then we'll start doing problems on this. First, I can do a thermodynamic process to a system without transferring heat, without adding or subtracting heat. No heat transfer. We call such process, we call it adiabatic process. Just bear with me. We're going to talk about this in detail in a minute. Okay. Another one is we can add heat or subtract heat from the system without changing its volume. So no change in volume, or let's just say constant volume. How about that? Constant. And that's called isovolumetric process or isochoric process, or isovolumetric process. Okay. Another one is we can also take or add heat to the system at constant pressure. Okay, and that's called Isobaric process. And the last one is that we can add or subtract heat at constant temperature. In other words, or change the volume or change the pressure at constant temperature. And that's called isothermal process. We'll take them one by one. And while we're taking them one by one, we're going to be applying the first law of thermodynamics, this one. Okay? All right. Let's begin with the adiabatic. So adiabatic means I am, let's say, changing the volume or changing the pressure or changing the temperature without adding heat or subtracting heat from the system. You get that? An example of that would be, again, I like the cylinder piston system. So imagine you have a cylinder piston system. Here is the cylinder, okay? Here is the piston. Imagine I cover the whole system with an insulation like that, thermal insulation. In this case, I am not allowing heat to escape or enter the system. So in other words, Q here is 0. Okay? No heat enters or leaves system. Got that? Okay? So let's say, for example, here's the gas right here. So let's say, for example, I exert the pressure to decrease the volume, for example, okay? Or maybe I expand it, or whatever I do. Well, what will happen to the temperature when I expand it? Well, it's going to drop down, right? It's going to cool off. And if I exert a force here, In other words, I've increased the pressure. What will happen if I increase the pressure and I push it this way? What's going to happen? The gas is going to increase. Excuse me, the gas temperature is going to increase, even though there was no heat added. You see what I'm saying? And this kind of process is called adiabatic process. So if I apply the first law of thermodynamics, which says delta U equals to Q minus W, and no heat added, so that means Q is 0. So in this case, the change in the internal energy is equal to the negative of the work. See that? And or you can just say the change is equal to the work in such a way that if the gas expands, then the work is positive, and delta U in this case is negative. And what will happen with the temperature? Is it going to increase or decrease when I expand? It's going to drop down, right? It's going to cool off. Okay. Now, if the gas compresses, okay, if the gas compresses, which means I'm going to take this piston and push it in, so I have done here work that is negative, and as a result of that, delta U is positive. Positive delta U, that means it's going to get hotter, okay? Remember, delta U and temperature are related, so if an increase in U means increase in temperature, a decrease in U is a decrease in temperature, and so on. So here the temperature is going to rise, so it's going to heats up. Okay, all right. The second process is isochoric or isovolumetric. Which means what? Same volume, okay? An ideal, what would be an example of something of the same volume? The pressure cooker, okay? I'm sure you have a pressure cooker in your kitchen. If you don't, ask your mother, she'll probably tell you about what a pressure cooker is. So, same volume, what does that mean? So the same, iso means same, by the way, same volume. What that means, again, imagine I have the same cylinder piston system, here it is. Okay, here's the piston. But what I'm going to do, I'm going to nail the piston like that. These are nails. You got that? And then I'm going to put it, say, under, flame. Here's a flame. I'm making a candle or something like that. So I'm heating it up. So what's going to happen to it? Well, what's going to happen is that heat is going to enter the system, right? Because of the flame, right? And remember, I am not allowing the piston to move. So therefore, what's going to happen? Heat is going to build up inside, and the pressure is going to build up inside. That's why, the pressure cooker, the one that your mother used to cook some maybe beans or something, the heat, it becomes extremely hot, and it is under extreme pressure, so the food cooks much, much faster. That's basically the function of a pressure cooker. But that's an example of isovolumetric process or isochoric process, where you are not allowing the volume to expand. Now, go back to a couple of pages back. Remember, we talked about no change in volume. It means what? Work is 0. There's no work. Remember, work is related to the change in volume. Remember that? See, remember, temperature related to the change in the internal energy, work related to the change in volume. Please write this stuff down. Very, very important, okay? So here we have delta V is 0 because it says it's an isovolumetric process, okay? So we're not allowing the volume to expand or shrink. We are nailing that thing, okay? Just like the pressure cooker. So now we have pressure is building up and temperature is building up as well. So now if I apply the first law of thermodynamics to it, so I have, it is delta U equals Q minus W. Well, W is 0 because W is directly related to the volume, change in volume. So basically, the change in the internal energy is really Q is equal to Q here, okay? Oh, and by the way, if I'm going to draw that on the PV diagram, how is it going to look like? Here is the PV diagram. Remember the PV diagram? And this is in meter cubed. This is pressure in Pascal. And so if I have here, remember the formula says PV equals nRT. So T have increased in the isochoric process. Volume, there's no change in volume. Remember, this is V, not delta V. Delta V is 0, but V is some value, okay? I mean, there is a volume right here. Look at that pressure cooker inside. There is a volume here. So I'm starting at some volume right here, okay? And then I have increased the pressure enormously up until some point right here. So from P2 to P1. As you can see, it's a vertical line. Why is it vertical line? Because the volume is the same. Some value here. See, if I go like this, then that means the volume have increased from some V to another V. You see what I'm saying? That's not what we're talking about. I'm trying to erase it again. Let me stop the video and come back. So for isovolumetric process, keep in mind that the work is equal to 0. You got it? Okay. Let's move on to the next process. And that is isobaric. Isobaric means same pressure. Okay, so the way it looks on the PV diagram, you can stop the video and kind of try to guess how it looks like. It's the same pressure. So I'm starting with some volume right here. And then same, sorry, V1 I wanted to write, and the same pressure, so it's just going to go like that until it is a some volume here, later volume, V2, and I go, let's say, from here, from point A to point B, and but it is the same pressure. You see what I'm saying? That's basically what's happening here. An isobaric basically would be something like, let's say you have a cup of water, okay, and then you want to heat it up. You want to make tea. So you take the cup of water, you put it in the microwave, okay. You turn on the microwave, and you wait for the water to heat up, okay. So what's going to happen to the water? It's going to expand. It's going to heat up, and it's going to expand in volume, correct? It's going to rise up. It's going to expand in volume a little bit. I mean, it's not closed or anything. It's just going to expand. But it is still under, since it's inside the microwave is not a pressure cooker or anything like that. It's open to the atmosphere. So even before I turn on the microwave, the pressure inside the microwave, let's say it is atmospheric pressure. Now when I turn it on and I have the water in there, it's still under atmospheric pressure. So nothing really happened. You see what I'm saying? So the pressure is still the same. In other words, whatever you cook in your kitchen, and you have a pot and you're cooking whatever soup or something, it is under the same pressure all the time, unless you cover it with, you put a lid on it, and then you are increasing the pressure, like when you make rice or something. But it is under, so that's a process of isobaric process where the pressure does not change. In other words, delta P is 0, not P0, delta P0. You get that, the change in the pressure, and as a result of that, of course, you get the volume would change. Say the water would expand, or the food would expand, or whatever. Okay, so cooking on a stove or a microwave. So nothing really happens. So you still have delta U not necessarily 0, delta V not necessarily 0, and of course you have work and it's not necessarily 0. Okay, so basically the formula PV equals nRT is valid, and the first law of thermodynamics, delta U equals to Q minus W. All these three items, none of them go necessarily to 0. Okay, none of them. The only thing is that when you want to calculate the work in this case, you want to use the first law, the ideal gas law, which is P delta V. Okay, so pressure times V final minus V initial, and that will allow you to get the work associated with it. Okay. All right, and the last process is isothermal process. Isothermal means I am not allowing the system to change its temperature. So I can, let's say I want to expand the gas inside the cylinder piston system, or compress the gas, but I am not, I'm going to keep the temperature exactly the same. Well, how do I do that? Well, let me show you. Let's say, for example, I have, let's say I have a cylinder piston system here, okay? Here's the cylinder, here's the piston, and let's say I prepare it to be at a certain PVT, right? All right, and let's assume I want to decrease the volume. So I want to compress it. I'm going to push it with a force and compress it down to here. So this is, I'm starting with some V1, and now I want to compress it all the way to V2. Of course, I'm going to have a different P2. And of course, I am going to have a different, let's say this is P1 and T1. And I'm going to have a different T. But I want to keep the T to be 1. How do I do that? How do I keep the same temperature? I mean, obviously, when you compress a gas like that, you're going to increase its pressure, you're going to increase it, decrease its volume, and as a result of that, it's going to heat up. Makes sense, it's going to heat up. Well, how am I going to keep the same temperature? Well, here's a little trick. Imagine I take the whole system, this one, and put it in the side of the refrigerator, or maybe I put underneath it ice cubes. Imagine these are ice cubes. So the amount of ice cube, the amount of ice underneath it, just enough to compensate for the increase in temperature. Just enough to absorb the increase in temperature. Remember, the cylinder is not insulated. You see what I'm saying? So I put it, so that increase in temperature will be immediately absorbed by the ice cubes. You get that? So it'll keep it right at the same temperature. That'll be one way to keep the temperature the same. Okay, what about if I want to expand it? Same thing. So let's say I have the same system, and now I want to expand it. And let's say I want to expand it all the way up here. So I'm going to pull it with a force, and I'm going to expand it. So, well, how do I do that? Well, how about if I put it under a heat reservoir, let's say on a stove. So I have here heat. I'll put on flame like that. These are flames. Okay. Of course, the number of flames or the amount of heat here is just enough to compensate for the the decrease in temperature. Okay, in such a way that I will keep the temperature to be delta T will be equal to 0. Delta T equals 0, not T equals 0. The change, there's no change in sign. This kind of process is called isothermal process. You get that? Isothermal process. And if I go back to my ideal gas law, so if you the one that will change in the pressure will change, the volume will change, but NR and T will be the constant. See what I'm saying? So it will look something like that. This nRT is constant because I'm keeping the temperature the same. That's the reason why we call it isothermal. So in this case, I'll have P equal to constant divided by volume. I'll have formula that looks something like that, okay? Well, if I'm going to graph this formula on the PV diagram, how is it going to look like? Well, if you go back to algebra, back in algebra, if you remember, if your teacher asks you a graph 1 over x, how does it look like? It looks like that. It's 1 over x. If you remember that. Well, that's exactly what I have here, 1 over v. So the isothermal process looks something like that. So here, I'm starting at a certain volume, V1, and I have increased the volume, V2. We're talking here about which one? I have increased, so that means I'm talking about this one, in this case. I have increased the volume, and as a result of that, what's going to happen? Well, I'm starting with some pressure, P1, and now the pressure went down by an amount, P2. And I can calculate the new pressure by taking this formula right here, and I can just say P1 V1 equals P2 V2. And this formula specifically helps me calculate the new volume, excuse me, the new temperature, I'm sorry, the temperature the same, the new pressure or the new volume for, you know, for the isothermal process, okay? Okay. I'm going to show you some examples and tell you how all of that works. I have at least 3 examples. I'm going to talk about them, and then we still have a second law to talk about. I may end up doing another video. I don't think I can finish all of that before I have 2 hours, but we'll see. Like I said, those 2 chapters are very, I mean, they're big, the 2 chapters. Okay, the name of or the title of this example is Isobaric Process. Now, in those examples we're going to be using, excuse me, we're going to be using the first law of thermodynamics to solve them. You see what I'm saying? All right. It says here you have gas enclosed in a container with a piston, and the area of the piston is equal to 0.1 meter squared. Okay, and pressure is maintained at constant. So pressure maintained constant at 8,000 Pascal. Okay, while heat is slowly added. Okay. Now the piston is pushed up 4 centimeters. Now here's the question. He said if 42 joules of heat is added to the system, what is the internal energy of the system? Okay. Okay, so let me explain what that means. So let's say we have here a cylinder piston system. Here's the cylinder, here's the piston right here. Here's the gas. He says the gas is enclosed in the container, and then we have the area of the piston is 0.1 meter squared, and then you have the pressure inside is maintained at 8,000 Pascal. Okay, and then we are slowly adding heat to the system. Okay, that's what it says. So what's going to happen when you add heat to the system? Well, as a result of that, especially if the system is free to move up and down, so what's going to happen? The piston is going to move up. Okay, but we want it to move just enough to keep the pressure exactly the same with no change. Okay, this is an example of the isobaric process. So what happens here is that the piston moves up, let's say up to here, where delta P is maintained to be 0. Okay, so we are maintaining the pressure to be 8,000 Pascal. So any change of that is 0. You get that? Okay, now he said if it moves up a distance, he says Okay, he said, while heat is slowly added, the piston is pushed up 4 centimeters. So it's going to move up by 4 centimeters here. And then he said, if the amount of heat, the Q here, is added is 42. So this one basically is what? Is Q. Okay, if 42 joules of heat is added to the system, now he's asking for what is delta U? Get that? Well, we can just use first law of thermodynamics, Q minus W. You see what I'm saying? What is W? W is P delta V, right? I just told you about it when we covered isobaric process. Let me go back. Isobaric right here. See that? Isobaric work V delta V, excuse me, P delta V right here. See that? So this is how we're going to calculate that. How do I calculate that? Well, he gives me delta Y. Remember we said that delta V is A delta Y. Remember that? The beginning of the video. He gives us both. He said the area is 0.1 and delta Y is 4 centimeters, so that's 0.04. And there we go. We have the volume, which is 0.1 times 0.04, and that will be equal to, what is it, 0.004 meter cubed. So now I can find W. W is the pressure, which is maintained at 8,000, times 0.004. So I can calculate the work equals 32 joule. So delta U, which is equal to Q minus W, so that will be, he said, what is it, 42? 42 is given, minus 32, and that will be 10 joules. So the internal energy gained 42 joules. In other words, that's how much heat has been absorbed by the molecules and the atoms of that gas. And as a result of that, the temperature has risen. Okay, that? Okay, here is a side question to this example, aside. If Q added while piston is clamped, or if you will, nailed in a fixed position, in other words, I am not allowing the piston to move. I'm not, what does that mean? It means I am keeping the volume constant. This is an isochoric or isovolumetric process. Okay, so now he's asking the question, what is W and what is delta U in this case? Okay, let me show you a picture. So here it is. Here is the piston right here. Here is, excuse me, the cylinder. Here is the piston right here. And what I'm going to do, I'm going to put a nail. I'm going to nail it like that. Okay, I'm not going to allow it to move. So that means there is no change in volume, and therefore delta V is 0. Make sense? And what does that mean? This implies that W is 0. So now if I go back to my first law, delta U, which is equal to Q minus W, well, W is 0, so therefore the change in the internal energy is completely absorbed. Excuse me, yes, that change in the internal energy is basically equal to all the energy that has been added to the system, Q, which is given to us as 42. You see what I'm saying? So delta U is equal to 42. Get that? Okay. Next example. Okay, this is an example of a isochoric or isovolumetric. process. Okay. It says I have water with mass of 2 kilograms is held at constant volume in a container, basically a pressure cooker, right? In a container. While 10,000 joules of heat is slowly added by the flame. Which basically, this is really, he's talking about a pressure cooker. So you have a cooker, you put water in there, you want to boil it for whatever reason. You close it completely, you seal it, you put it on the stove, and now 10,000 joules of heat has been added there. Okay, so it's heated up. Of course, we're not allowing the pressure cooker to, the pot to expand, you know what I mean? So all that pressure buildup, temperature buildup in there. This is basically what the isovolumetric process is. Okay. So he says 10,000 heat is slowly added to the flame. Container is not, okay, however, it says here the container is not well insulated, okay, and as a result, 200 joules of heat leaks out. Okay, to the surrounding air. The question is, what is the temperature what is the temperature increase? I'm reading it wrong. What is the temperature increase of the water? Okay, that's what the problem is. You may want to pause the video and think about it. But because it is isovolumetric, that means what? Delta V is 0. That's immediately tell me work is 0, right? They're both related to each other. The first law of thermodynamics, delta U equals to Q minus W. That's 0, so delta U is basically equal to the heat added to the system. Now he says part of that heat is leaking, or is being leaving the system. So that means I want to know what is the net heat. The net heat that is actually going into the internal energy. Remember, it says here delta U is equal to Q, but that Q, not all of the Q. There is a 200 joule of heat is leaving the system, leaking. So in this case, the net heat is really, what is that other one? Forgot what it is. Oh, there it is. He said 10,000 right here. I'm sorry, I think I've read it wrong. The leaking is 2,000, not 200. Sorry, let me go back here. Right here, guys. He said the container is not well insulated, and as a result, 2,000 joule of heat leaks out, and as a result, you want to say here, as a result, 2,000 joule, okay? It's not 200. Okay, so it's going to be here 10,000 minus 2,000, so that basically 8,000 joule of heat is being converted into internal energy. You see what I'm saying? To the water. So therefore, delta U is equal to, in this case, 8,000 joule. Okay? Okay, so I have that. Now he's asking the question, what is the corresponding temperature? What is the increase in temperature? How do we do that? Well, go back to chapter 14. We said that Q is equal to mc delta T. And this, of course, this Q, which is equal to the Q net, and is also equal to delta U, right? So we can easily find delta T. That'll be Q over M times C, or if you will, delta U over M times C. So delta T is equal to, delta U is 8,000 divided by the mass of the water. He gives it to us. He says 2 kilograms. And then you have the specific heat of water. Look it up. It is 4.186 times 10 to the third. And then we calculate all that. So delta T is equal to, if I calculate all of this, I'm going to get 0.96 Celsius or Kelvin. They both, remember, the delta is the same. And there we go. Okay. Okay, one more problem. The last problem I'm going to do before I end this video. I still have to cover the second law of thermodynamics. That's going to be part 2 of the video. So I'm going to do another video. So let me do this example and then we'll finish this one. Okay, as I said before, I cannot exceed 2 hours. Otherwise, I'm not allowed to publish it. Okay, the example, the title here is boiling water. It says that 1 gram of water occupies 1 centimeter cubed at atmospheric pressure at 1 atm, is that right? At 1 atm. When this water is boiled, it becomes 1,671 centimeter cubed of steam. Okay? Question. Calculate the change in the internal energy of this for this process. Calculate the change in the internal energy for this process. Okay? So let's read it again. He said you have a 1 gram of water, really tiny amount, just maybe a drop. 1 gram of water occupies 1 centimeter cubed at 1 atm. Okay. When this water is boiled, now we take this water and we boil it until it turns into steam. Okay, and now the steam is occupying a huge volume of 1,671 centimeter cubed of volume. He said, what is the change in the internal energy, delta U, for this process? Okay, so the first thing I need to do, well, okay, so let me write it down. So you have delta U is Q minus W, is that right? Now here you agree with me, it is isobaric because you are basically boiling water and there is no change in volume. So that's an isobaric. So the work in this case really is P delta V. The delta V basically, here is the first volume right here, 1 centimeter cubed, and the second volume is that. So I know what delta V is, of course, converted to the proper unit. And then you have atmospheric pressure. So I can easily find that. There's no big deal. I found W, no problem, because that's an isobaric process. The problem here is Q. Well, what is Q? Well, Q is that I'm starting with 1 centimeter cubed of water, and now it's being converted into 1,671 of steam. Okay? So that's basically what we call the latent heat of evaporation. Make sense? So this Q really is just that's how much water to evaporate. Excuse me, how much energy needed to evaporate it. So Q here is the latent heat of evaporation. So that's M sub V, and the mass here is 10 to the negative 3 gram. Remember, this is a kilogram here. You said it's 1 gram right there. See that? So multiply that. The latent heat of evaporation. You need to look it up. I have it right here in front of me. 2.26 times 10 to the 6 joule per kilogram. Go back to chapter 14 video. We talk about all of that in details. And then there we go. I know how much heat has been added, 2,260 joules of heat, okay? And the work, I just go back and take this one right here. So that's P delta V. And the pressure is 1 atm, which makes it, just convert it into, whoops, I'm having a difficulty erasing again. Bear with me, I'm sorry. Here is how. I'm going to do it without cutting the video. Basically, you'll quit OneNote, and you bring it back again, and the stupid thing would work. Let's do it again. It should work now. I don't know why it does that. There we go. Okay, so we have the pressure is 1 atm, which is 1.013 times 10 to the 5th, multiplied by delta V, which is basically the difference between the two numbers, of course converted to meter cubed. So that's going to be 1671 minus 1 centimeter cubed, so that's times 10 to the negative 6 meter cubed. You see what I'm saying? And then we calculate the work. And when we do that, I have already done it, 169 joule of work. Okay, so I got the Q value, and I got the heat added to the system, and I get the work, and that's it. So the delta U in this case is Q minus W, and that will be equal to 2260 minus 169. Calculate that, and that will give me 2100, 2123, yes, I think so, 2000 delta U. And that's the rise or the increase in the internal energy. Okay? All right, I'm going to stop here for this video. Please click on the next video once it is created.